In this short video, I will do it once more, similar to what I did in the previous two videos, but I will consider another input to my Unity feedback system. In the previous two videos, we analyzed it for step input and for ramp input. Now we will do it for unit parabolic input, where unit parabolic input is defined, as you can see in this slide, where this input is equal to t squared over 2 for non-negative t. And with this input, we can analyze the steady state error for a unity feedback system. So same like before, we will analyze the steady state error because of this unit parabolic input using the final value theorem. But in this case, because we are considering a parabolic input, and as we know, a unit parabolic input in Laplace domain is equal to 1 over s cubed. Therefore, the steady state error because of a unit parabolic input will be equal to limit s to 0 for 1 over s squared times gs. Now I will define a new variable, the so-called static acceleration error constant, or Ka. If I define that Ka is equal to limit s to 0 s squared times gs, referring to the steady state error that we discussed already in the previous slide, we can redefine the steady state error because of unit parabolic input to be equal to 1 over Ka, where Ka again is the static acceleration error constant. Acceleration error is anyhow is not an error related to the parabolic input, but it's the error in position. Now, how this Ka will differ for different type number in our unity feedback system. Let's consider now if we have a type 0 system in our unity feedback system, because the absence of poles that is equal to 0 in our type 0 system, the static acceleration error constant will be equal to 0 if we substitute 0 to all of the s's in this equation, right? Similarly, for type 1 system, the Ka will also be equal to 0, right? Because we only have one pole that is equal to 0 in our type 1 system. Now let's consider type 2 system. For type 2 system, we have two identical poles at the origin. This s square will be cancelled by this s square, and then at the end, the static acceleration error constant will be equal to the DC gain of the open loop transfer function. So in type 2 system, the static acceleration error constant will be finite. But then for type 3 or higher system, similar like what we did before, because we have poles more than 2 that are equal to 0, at the end the static acceleration error constant will be equal to infinite. Those are the values of Ka for different type number. What will be the effect of this type number to the steady state error because of the unit parabolic input? We have already defined it before that the steady state error in this unit parabolic case will be equal to 1 over Ka, or the steady state error technically is just inversely proportional to the Ka. In this case, the steady state error because of unit parabolic input will be equal to infinite when we have type 0 or type 1 system, which means the systems here, either type 0 or type 1, will not be able to follow the unit parabolic input. On the other hand, in type 2 system, because we have a finite static acceleration error constant, the steady state error will also be finite. It will be equal to 1 over k, where k is the DC gain of the open loop transfer function. So in this case, again, for type 2 system, the output of the system will be able to respond to the unit parabolic input, but it will contain some constant error when the steady state condition has been reached. While for type 3 or higher systems, we will have a zero steady state error when a unit parabolic input is given, which means, again, when the steady state error is reached, the output will be able to follow the input very well with zero steady state error. So again, here I want to highlight it a bit more detail. For type 2 system, we will always have a finite steady state error when a unit parabolic input is given. It is illustrated in the next slide. So this is a typical response of a type 2 system if a unit parabolic input is given. This is the unit parabolic input, and the bold black curve here is the response. As you can see here, when the steady state error is reached, we will have a constant steady state error. Okay. To conclude, then, both type 0 or type 1 system will not be able to follow parabolic input in the steady state condition, while for type 2 system, the response can follow the unit parabolic input, but with a finite error in steady state condition, of course. While for type 3 and higher system, the response will be able to follow the parabolic input perfectly without any error in the steady state. To conclude again what we have already discussed in the last 3 short videos, the conclusion can be seen in this slide. How to interpret this table? This table says if a step input is given to a unity feedback system, okay, we will have a finite steady state error if the unity feedback system is considered as a type 0 system. When we have type 1 system, the steady state error will be 0, as well as for type 2 and higher. If a ramp input is given to a unity feedback system, we will have infinite error if we have type 0 unity feedback system, which means the system will not be able to follow the ramp input at all. If we have type 1 system, we will have a finite error and at the steady state condition when a unit ramp input is given. For type 2 or higher, we will have zero steady state error for a given unit ramp input. If a parabolic input is given to the unity feedback system, if we have type 0 system and type 2 system, these systems definitely cannot follow the parabolic input at all. For type 2 system, it still can follow the parabolic input, but with a certain finite steady state error. This is how to interpret this table. In this slide, I will summarize what we have already discussed in the last 3 short videos. Kp, Kv, and Ka, static position error constant, static velocity error constant, and static acceleration error constant describe the ability of a unity feedback system to reduce steady state error. And these values are a good indicative of steady state performance, right? It is generally desirable to increase error constant because the higher the error constant, either Kp, Kv, or Ka, if we have a finite steady state error accordingly, the steady state error will decrease. So it is desirable definitely to increase the error constant. In order to improve steady state performance, it is desirable to increase the system type. So this agrees with the slide that we discussed before, that I showed to you before. If a unit step input is given to a unity feedback system, if we have type 0 system, we will have a finite steady state error, but somehow if we can increase the type number of the system from type 0 to type 1, the steady state error because of a unit step input will be reduced to 0. Same thing applies to any other inputs, right? So to highlight again this summary, in order to improve steady state performance, it is desirable to increase system type through the addition of integrator. What I meant by integrator here is an additional of S in the denominator of the open loop transfer function, or in other words, the addition of poles at the origin in our open loop transfer function or forward loop transfer function. Both of them are the same for a case of unity feedback system. An introduction of an integrator, even though this means the increased number of the type system, it will give a risk to destabilize the closed loop system. So be careful here. Indeed, we can reduce the steady state error by introducing more integrator, but this might also cause instability in our system at the end. Designing a satisfactory system with more than 2 integrators in general is difficult. So at most, in practice, we only add 1 integrator in our unity feedback system. Starting from 2, adding 2 integrators, it is becoming more difficult, in particular, to maintain the stability of the system. This slide concludes our discussion in system type. I will just give one more slide here, a reading assignment. Please refer to this textbook, Modern Control Engineering. in particular, please take more attention on section 5.8. Okay, thank you and see you again in the next video.